Okay, we start. So I'm Hiroki from Tokyo Institute of Technology in Japan. So my title is the long-term change of universal summer climate index estimate from weather station, climate model, and decision trees. Okay. So first I'm talking about the introduction. So this figure shows the change in deaths due to heat stroke and cold stroke in Japan. So from this figure, so you can say the number of heat stroke and cold stroke cases has been increasing every year in Japan. Why about increasing? So to consider that, so it is important to understand the summer comfort, spatial, temporal pattern, and terrain. And the main research have been developed a lot of summer comfort indices to understand the summer comfort. Then keynote speakers say that UTCI. So UTCI was developed. So UTCI can be applied on all climates and seasons. Then it can be calculated from air temperature, radiation, and wind speed and humidity based on Ferrosca model. It's called UTC Ferra model. So nowadays, the American researcher studied the summer comfort by using a lot of summer comfort indices. So however, in Japan, almost no study have been investigate long-term changing summer comfort at a nationwide scale with a wide climate condition. So long-term analysis of the summer comfort are helpful to take measure against the impact of global warming and urbanization. Then this objective is the evaluating the long-term changing of outdoor summer comfort over Japan based on nationwide weather station network. So however, there are one challenging. So it is the detailed UTCI data across Japan. So as I said, the UTCI calculation requires the temperature, wind speed, humidity, and the radiation. So radiation is the mean radiant temperature, so MRT. So however, Japanese weather station does not observe the radiation. So we should calculate the MRT by using the weather models if we want to get the detailed UTCI. So however, the weather models such as the WAP model requires a lot of computational resources at a fine scale. So in this study, so long-term high spatial simulation of Japan is not possible. To solve that, we incorporate the machine learning model techniques to estimate UTCI, specifically for the MRT. In accordance with the social background, the objective, and the issue, there are three specific aims in this study. So machine learning aids the UTCI estimation at the national weather station for a long term and evaluate the long-term UTCI across Japan and investigate the relation between the UTC and the heat stroke cases. Then next is about the method. So target area is the 140 weather station points. So it's called the Amedas in Japan, and the time period is from 1980 to 2020. Then regarding the machine learning to estimate the fine scale MRT, so this machine learning model purpose is to get MRT value close to rough output at Amedas point. Then this model was developed by using the XGBoost. XGBoost is one kind of boosting decision tree algorithms. It's the powerful algorithm. Then this figure shows the developing the machine learning model flows. So target value is the MRT from WAP model. Then feature values is the temperature, humidity, L5 radiation data, and like that. Then this figure shows the UTC calculation flow. So first, the fine scale MRT at the MLS point was calculated by using the machine learning. Then error file validation data and Amidas data are used as an input data of the machine learning. Then UTCI calculation by using the Amidas data and machine learning output. Then result. So first, I confirmed the accuracy with the machine learning model. So this figure showed the comparison between the MRT from error 5 and the machine learning and the WAF model. So red is the machine learning output in Tokyo and Osaka. There are two data are now used for training machine learning, and that table shows the accuracy for the machine learning model. So from then, the machine learning model is able to output MRT value close to WAF model. However, I should consider accuracy varies by region. Actually, the Osaka does uh, not good compared to Tokyo. Then I'm going to show the UTCI result. So this figure shows the change in the non-summer stress days in three cities in Sendai, Tokyo, and Osaka. Then non-summer stress means the UTCI value is between 9 degrees Celsius and 26 degrees Celsius. Then the number of non-summer stress days in summer decrease. Actually, in Sendai and Tokyo, the the day decreased by about 30%. In winter, the day increased. Actually, in Osaka, increased by about 20%. So where increased? So this is because the UTCI value have been increasing. So I confirmed it. So this figure shows the trend of UTCI in summer. So I conduct the one down test to confirm whether each station have trend or not, from viewpoint of statistical analysis. Then as a result of one down test, 98 points have a trend. Then UTCI increase at all point. Then large increase in trend located in not only urban area and but also rural area. Then regarding the relation between UTC and heat stroke cases, so in three cities, so and the table shows the threshold. Threshold means the UTCI value at which heat stroke cases dramatically increase. So from then, even though UTCI value is the same between cities, the heat stroke case risk is different. So we can say there it is important to consider the local characteristics when we take measure against the health risk due to global warming and the urban heat island effect. Um, about in winter, 5 point of a trend, then 33 points have the increasing trend. On the other hand, 20 points have a decreasing trend. So actually, the colder region have more cold source in winter. Why? So this because the wind speed trend. So colder region have the increasing wind speed trend. So this means the wind speed increasing wind speed trend make colder source in winter. So that's why. So it is important to consider changing the wind speed as well as the changing temperature and the MLT in winter. Then conclusion. So in this study, I proposed the machine learning to estimate the fine scale MLT. So this method can be applied on not only Japan but also other areas. But I should improve this model accuracies. Then I evaluate some UTCI trend in Japan. So in summer, the summer comfort has been worsened, not only in urban area and but also in rural areas. Then UTCI threshold of the yes, that's all. Then yeah, we should consider the local characteristics. Yes, that's all. Thank you.
Thank you very much, and thanks for keeping to time. So, have time for a quick few questions. One over here.
Hello, I'm Mr. from Taiwan. Just a very quick question about the integrated temperature calculation. Because you have already the upward and downward the radiation from the EI5 data. So why you require machine learning to calculate the integrated temperature? Because there was already some statistical mechanism or process use downward and upward radiation to calculate the integrated temperature. So why you require machine learning?
Thank you for the question. So, yeah, as I said, so to be honest, I want to calculate by using MRT by using the WAF model. So, however, so the weather model requires a lot of money and the computational resources. So, to avoid using the WAF model, I developed this machine learning model. It's,
Sorry, I'm not here. For what purpose?
the purpose is, I said,
Questions you might not be able to find directly.
I see. Your purpose is to get the MRT value called the WAF output. So, yeah, of course, the way is to use error 5. However, the weather station point is located to one grid of error 5. So that's why, to avoid that, like, so I want to get the fine scale MRT values.
Okay.
Yeah.
I think we have to, maybe you can discuss after, but
Yeah.
I think we have to move on for the next, to keep to the schedule. But thank you.
Yeah, thank you.
Okay, our next speaker is Dr.